Hello there! This lecture is all about regression. And regression essentially takes correlation a step further and uses the relationship between two variables, which is what correlation is all about, to predict values for the dependent variable based on values for the independent variable, or predict values for y based on values for x. So in correlation, remember you used correlation analysis to describe the linear relationship between x and y in terms of direction and strength. So remember, direction, be positive or negative. If the two variables are changing in the same direction, be a positive relationship. If they tend to change in opposite directions, it's a negative relationship. That should just be a review from the last lecture. And remember, strength, the closer the correlation coefficient is to 0, the more scattered the data points are on the scatter plot, the less consistent, the less relationship there is, and the closer that the correlation coefficient is to the absolute value of 1, be it positive or negative, the stronger the relationship is. The data points tend to fit a straight line, and there's a more consistent relationship there. Well, again, regression is moving on to predicting y values based on the relationship between x and y. So, like ANOVA, regression models help you answer questions by handling all the clutter resulting from all the differences or the variation, by revealing patterns, so you can see if there's systematic, predictable, explained variation in y that's based on the relationship between x and y. And this pattern tells us what we can anticipate in new data and goes beyond just describing the data that we can observe. So we're still going to do hypothesis testing to see if the regression equation, this equation that we're going to come up with to predict y, if we think that those predictions would hold up in the population at large. So, a summary of the topics that will be covered in this lecture. So I'll show you a simple example of the linear regression equation in a scenario where you'll have exact perfect correlation. So where the linear regression equation, and the regression equation results in the plotting of a straight line, where that straight line actually fits the data perfectly because there is a perfect correlation. Then I'll give you a review of how to calculate the correlation coefficient, because it is an important first step to calculating the regression equation. And then I'll show you how to use that regression equation in practice to make predictions of what you think the value of y would be based on the value of x and the relationship between x and y. Then we'll go over the standard error of the estimate, and then finally hypothesis testing with regression. So here is the linear regression equation right here. So this little y hat is what we'll call it. This stands for the predicted value of y. Then this x, that is the thing that is going to remain a variable in this equation. So you're going to solve for b and you're going to solve for a. And then you're going to have a regression equation that says y hat equals some value times x plus some value. The reason that this x remains x in the equation is because you want to be able to plug in any given value of x into this equation to figure out what the predicted y would be. B represents the expected change in y for each 1 point increase in x. So as x increases, what do we expect to happen to y? That's what b is. It's also called the slope or the weight. It's really called the weight in terms of regression. But if you remember the slope-intercept formula from algebra, this is like the m. So remember y equals mx plus b? That was algebra. Now, of course, the statisticians don't want to use that formula because we like to make it confusing for you. So b is like the m in the slope-intercept formula for algebra. It's called the slope in algebra. It's called the weight in statistics. Same concept, though. And then a is the constant, or in algebra terms, the intercept. So a represents the value that would be predicted for y regardless of the value of x. So it's kind of like the starting point for your predicted values of y. In algebra, you'll remember that a is the value for y when x is 0. So here's a really straightforward, simple example of the regression equation in practice when we have a perfect correlation, when there is a perfect consistent change in y for each 1 point increase in x. Here's an example. So let's say that college students pay a fee of $150 per semester, and they also have to pay $148.75 per credit hour. Well, this $150 per semester, this is our constant, right? No matter how many credit hours they're taking, no matter what the value for X is, so in this case, credit hours, the number of credit hours will be X, you're going to be paying that fee of $150. So in this example, 150 would be like our A, our constant. X is going to represent the number of credit hours. So we can plug in a number of credit hours to figure out the tuition. So that would be our Y hat as tuition. And then this 148.75, this would be our B in our regression equation. So this is akin to the change in tuition for each credit hour that is added to your semester. So just to break it down, in terms of the regression equation that we just looked at, Y hat is going to be the predicted tuition. In this case, the prediction is going to be pretty darn accurate because there's a perfect relationship. B is the cost per semester. X is the number of semesters, and A is the fee that's allocated every semester, regardless of how many credit hours you're taking. So if you're taking 3 credit hours, your predicted tuition, or your actual tuition in this case, remember because we have a perfect relationship, is $148.75 times 3 credit hours. So this is how much you pay per credit hour, plus that fee that's constant. When you do this math, you end up with $596.25 per semester if you're taking 3 credit hours, which is equal to $198.75 per credit. Then check it out. If we're doing 6 credit hours, the value for B and the value for A remain the same. You'll see that for all of these. The only thing that changes is that value for X. Now we're talking about 6 credit hours. So you solve for that. You end up with $1,042.50 per semester, or $173.75 per credit. This little per credit thing in there is not going to be important. I'm not going to have you break it down that way, but I'm just putting it there as kind of a little lesson that it may behoove you if you are mainly concerned about finances and you actually have the time and the resources to take a lot of credit hours. It's nice to take more credit hours because in the long run, if there's a fee per semester, you're going to pay less per credit because that fee is being split up among more credit hours. So that's why I break it down per credit. But in practice, when I have you use regression equations to predict the values for y, you'll just be giving me something like this value here, the final value once you plug x into your equation. So you can see that for every increase in credit hours, there's a $148.75 increase in tuition. So it's a perfect linear relationship. These are your data points, if you plot this out, and your data points in your regression equation are equal to plotting x and y hat. So x, in this case, was 3. The y hat that we came up with, or the predicted tuition, 596.25, right around here, boom, there's your dot. Well, in most cases, your data is not going to fit a straight line. But your regression equation is always going to fit a straight line when you plot it out. So in a more realistic example, you're going to have data plots that are all over here in your scatter plot from your actual data. And then the regression line, based on the equation that you calculate, will fall right in between all those dots. Because remember, if you don't have a perfect correlation, your data doesn't fit a straight line. But the regression equation will result in a straight line that'll give you the best prediction possible based on all the variation in the relationships between x and y in your data. And that'll make more sense once we do another example. So let's go ahead and do an example. So this is going to be a situation, spoiler alert, where our data is not going to fit a perfect straight line. It's not going to be a perfect correlation of 1 or -1. So there is going to be some variation between our data points in our scatter plot and then the actual regression line that we're going to plot based on the equation that I'll show you how to calculate here in a minute. All right, so let's do this first. So I actually collected some data in the past in a statistics class where I asked students to tell me what they thought their grade was going to be on the quiz when they turned it in. And I calculated that data from a random selection of 5 students and then compared it to the actual grade that they got to see if students are actually able to predict what their quiz grade will be. So the first thing that often happens in a regression calculation, you calculate a correlation. For one, it tells you how far off you think your predictions based on your regression equation are going to be. The more spread out your data points are, the lower value, the weaker your correlation is, the less effective your regression equation is going to be for predicting relationships in your data, or predicting, in this case, earned quiz grade based on expected quiz grade. Also, most of the calculations that you use in the correlation will also be used in regression. So if you've already done your correlation, the calculations for regression are really simple and straightforward. All right, so let's go ahead and draw our scatter plot first, just to get a nice visual of our data. So in this case, our x value, our independent variable in this case, would be expected grade. I'm just going to call this expected. And then earned is like our dependent variable. And I'm going to go ahead and shrink my axes here. I'm not going to go from 0 to 50. I'm just going to work with the range that I'm given. So expected goes from 25 to 45. So I'll start with 25, go by fives, 30, 35, 40, and 45. Right? And then the y-axis ranges from 30 to about 48. So I'll start with 30, 35, 40, 45, and 50. This doesn't have to be perfect. It just gives you a nice rough picture of your data and what kind of correlation you'll expect, and now how much error you'll expect to see in your regression equation, or how much room there is between the dots in your scatter plot and the actual regression line that we'll draw in a little bit. Okay, so the first person, 25 expected, 35 earned. That dot represents them. Second person, 33 expected, 30 earned. Okay, 33 and 30, so roughly like here-ish. Next person, 35 expected, 45 earned, so about here. 42 expected, 40 earned, so 42 and 40 is like here-ish. And then 45, 48, so 45 expected, 48 earned. 45, 48, right around here-ish. So I'm looking at this data and I'm thinking this is probably a moderate relationship. The data points aren't too spread out, and it's clearly going to be a positive relationship. So when I calculate my correlation coefficient, I'm going to expect to have a number that's around, like 0.5-ish, and a correlation that's going to be a positive value. Okay, so let's go ahead and calculate the correlation. So the first thing I want to do is I want to write down all my formulas for correlation, and I didn't summarize them in this lecture because they were in the previous lecture, but I'm going to go and write them down. So let's start with R is equal to sum of products divided by the square root, sum of squares x times sum of squares y. So I need to have a formula for my sum of products, a formula for my sum of squares x, and my formula for my sum of squares y. All right. Sum of products, sum of x times y, minus sum of x quantity times the sum of y, divided by n. This one, sum of squares x, is sum of x squared minus sum of x quantity squared divided by n. Sum of squares y, sum of y squared minus sum of y quantity squared divided by n. Okay? Start from the bottom, work our way up. Again, I already did the calculations, the preliminary calculations to find the sum of xy, sum of x squared, sum of y squared, sum of x, and sum of y, and the means as well, because we'll be using the means to figure out the regression equation. So I'll just plug in what I've got. Sum of y squared is 8,052. And I'm not going to go through how to get all those numbers because I've showed you before, and I've got all the calculations here. And it's actually 8,054, not 52. 54. Minus, okay, sum of y is 198 squared divided by, how many people do we have? 1, 2, 3, 4, 5. This becomes 8,054 minus, well, 198 squared gives you 39,204. And we're going to divide that by 5. 8,054 minus, well, 39,204 divided by 5 gives you 7,840.8. Okay, and then subtract, and you get 213.20 for sum of squares y. Again, at the end, you kind of want to write an equal sign and what you calculated so that when you plug it into your formulas, both for R and for your regression equation, and then eventually for finding the significance of the regression equation, you'll have it right there. Okay, now let's move on to sum of squares x. So all the x scores squared and added together gives you 6,728. The sum of x, all the x scores added together, is 180. I'm going to square that, divide by 5. So 6,728. 180 squared gives you 32,400. Divide that by 5. So you get 6,728 minus 32,400 divided by 5 gives you 6,480. And you subtract and you end up with a nice whole number of 248 for sum of squares x. Moving on. Sum of products. So the sum of x times y, each x times each y for each person, added together, 7,280. Sum of x is 180. Sum of y is 198 divided by 5. 7,280 minus 180 times 198 gives you 35,640. 35,640 divided by 5. 7,280. So 35,640 divided by 5 gives you 7,128. To do some subtraction, you end up with the sum of products. Oh, another whole number, 152. Done. Now we're ready to figure out our correlation. How exciting. We can see if our correlation coefficient matches our prediction. All right, 152. So we already know it's going to be a positive value, which is great because that matches our picture. So I'm feeling good. All right, sum of squares x was 248. Sum of squares y is 213.20. Okay, 152 minus the square root. So 248 times 213.2 gives you 52,873.6. Then this becomes 152 divided by, well, the square root of 52,873 is 229.9426. And you end up with a correlation of 0.661. So this is a strong positive relationship, but the main thing that I want to point out, because this is all about regression, we know that the correlation is not equal to 1. So there is going to be some error in our regression equation. Or in other words, we're not going to expect the predicted y value to be equal to these for all of these actual x values. And conversely, we're not going to be able to predict with 100% certainty, based on this data, what somebody's earned quiz grade will be based on their expected quiz grade. But rarely do you have a correlation of 1, and rarely is the regression equation perfect. But it's still useful to make, rough ballpark figure predictions of what you would expect y to be. So just because you don't get a correlation of 1 doesn't mean that you don't want to do the regression equation. The regression equation is really, really useful, even when you have a situation where you don't have a perfect relationship. So let's go ahead and find the regression equation. So the formulas to find the regression equation are equal to this. So remember, we've got this y hat equals bx plus a. So once we find a regression equation, we'll be replacing b and a with some value. Well, b, the formula for b, is equal to sum of products divided by the sum of squares x. Both values were found when we did our correlation. And then a, the value for a, our constant in this, is equal to the mean of y minus b times the mean of x. So remember, when we did our correlation, we found, and you have to find B first before you can find A, because B is part of A. So we found our sum of products to be 152. So 152 divided by sum of squares X was also found to be 248. You end up with a B of 0.613. So already, I know based on the data that I have from these 5 people, I would expect to see a 0.613 point increase on earned grades based on a 1 point increase in expected grades. So remember, B tells you the expected change in Y for each increase in X. So in other words, for each additional point that you would expect to get on the quiz, I would expect to see that you would have a 0.613 point improvement or higher grade on your earned quiz, or on your actual earned grade on your quiz. Okay, and the mean, I forgot to put that here. So the mean for Y, so adding up all the Y's, divided by how many Y's there are, that's totally review. Sum of X divided by N, 198 divided by 5, I had 39.6 for the mean of Y. And then my B that I just found is 0.613. Let's make that little minus a little clearer. And the mean of X, 180 divided by 5 is 36. So this becomes 39.6 minus, so 0.613 times 36 gives you 22.068. And you end up with an A of 17.532. So this is like our starting point for the earned quiz grade. So in other words, if somebody expected they were going to get a 0 on the quiz, we would anticipate that they would actually get a 17.532 based on this data and the regression equation that we're going to make with this data. So we now can write our regression equation. So 0.613x plus 17.532. So when you're asked to write the regression equation, you're going to be doing something like this. Remember, just finding a value for B and A and then rewriting it, keeping Y hat there, a predicted Y, and X as X. So this would be like our final answer for the regression equation. Now let's use that regression equation to predict what we would expect everybody, or what kind of quiz grade we would expect someone to earn based on all these expected grades on the quiz. Remember, don't get confused because I'm saying expected in 2 different ways. The expected grade is the grade that they thought they were going to receive. The earned grade is the grade they actually received. And we're trying to predict what their earned grade would be based on their expected grade. Now keep in mind, these little Y hats that we're going to use, they're not going to be identical to the actual values here because our correlation wasn't perfect. There was some error. Okay, so if somebody expected in the population, right, we're always doing inferential statistics, we're extrapolating this to the population. Based on this, and we don't know if it's significant yet, but we'll get there, what would we think somebody would actually earn on the quiz if they thought their grade was a 25 in the population? So let's use this regression equation. So Y hat equals 0.613 times 25 plus 17.532. 0.613 times 25 gives you, let's see, 15.325 plus 17.532. And I would expect that somebody would, or I would predict, let's use the word predict. I would predict that somebody would earn a grade of 32.857 on the quiz if they expected their grade to be a 25. So I'll do one more and then I'm just going to fill in the values because the math for this is pretty straightforward. So again, 0.613 is still B. Now we're going to do 33 for our X. A is still 17.532. 0.613 times 33 gives you 20.229 plus 17.532. And we would predict that somebody would actually earn a quiz grade of 37.761 if they expected to earn a grade of 33. All right. So the next one, if you do the calculations, and I encourage you to do them, go ahead and pause this video, try to figure out the last three predicted earned quiz grades based on expected quiz grade 35, 42, and 45. Okay, I'll give you the answers, and hopefully you got them right. 38.987, 43.278, and then 45.117. Now remember, I mentioned that these predicted values for the earned quiz grade in the population are not going to be identical to the to the actual earned grades in the sample because our correlation is not equal to 1. So we already knew we were going to have some error here, a difference between the y in our data and the predicted y in the population. And that's okay. Again, the regression equation can still be useful. We'll test the significance of it a little bit. But let's go ahead and plot this regression line into the original scatter plot to get a visual of where our predictions fall relative to the data in our sample. And I'm going to go ahead and use red to plot the regression line. And one thing I want to mention, you can pretty much plot the predicted y for the lowest value of x and the predicted y for the highest value of x and just connect the dots because it's a straight line. So if you draw a diagonal line, you're good to go. You don't have to plot every single x and predicted y to plot your regression line. So let's go back to our scatter plot. So the first one that I'm going to plot, so for the expected 25, remember I calculated expected grade on the quiz of 25, I calculated a predicted value of the earned grade to be 32.857. So 25 up to 32.857. So that'd be right around here-ish. And then the last one for the highest expected grade that I collected in my data was 45. We predicted they would earn a grade of 45.117. So 45 up to 45.117. So right around, I'm sorry, yeah, 45.117. So right around here-ish. And then you draw your regression line, connect the two dots, and check it out. It's pretty much smack dab in the middle of all of our dots. So if you think about back in the day when we were talking about the mean and the standard deviation, and mean was a measure of central tendency, well, you can think of the regression line as like a mean of the relationship between x and y. It's right in the middle of all those scatter dots. And then next we're going to talk about the standard error of the estimate. And that's going to be like the standard deviation or like the average spread of dots from the, what we can call, like the mean, the regression line. But before we do that, there's one last thing that I forgot to do here. So if somebody had a quiz or they expected a grade of 40, what would we predict that their earned quiz grade would be? So if x is 40. Because you don't just want to predict the values in the population based on the actual values in your data set. The regression equation is useful for predicting pretty much any value of y based on any value of x. One thing I want to point out though, you typically don't want to use the regression equation to predict values of y based on an x value that doesn't at least fall within the range of the data that you collected in your sample. All right, so if somebody based on this regression equation said, I think I'm going to get a 40 on this quiz. Well, we would think based on, again, the equation, y hat equals 0.613, x, in this case, is 40, plus 17.532. Well, 0.613 times 40 gives you 24.52. And add that to 17.532. and you get 40.052. 40.052. That is the predicted y in this case. Well, let's check our sketch of our regression line, and it should make sense that 40 expected would result in about a 40.052 predicted value. 40 up there, it's right around 40.052 where that expected is. It falls on the regression line. And as long as you're a decent artist, when you draw your scatter plot, you'll see that pan out. So for all the values that we could plug in within this range, for x, we would find an expected y that falls along this line. Okay, so now let's move on to the standard error of the estimate. And the standard error is always the expected difference, be it the expected difference between a sample mean and a population mean when you were doing t single sample or x, or the expected difference between two sample means when you were doing t independent measures. Standard error is always the difference to expect just due to chance. All right, so the standard error of the estimate tells you the degree of error associated with predicting y using this regression equation. So remember, the regression line won't always perfectly fit the data. So maybe someone with an expected score of 40 doesn't actually get a 40.052 earned grade on the quiz. Even if our regression equation is significant, which we'll test for here in a little bit, you're going to expect some error. And that amount of error that you would expect between any expected or predicted value of y and the actual value of y that you'd see in the population, that's your standard error of the estimate. So again, it's kind of like a standard deviation in terms of the spread of dots from the regression line. And not just the raw spread in dots, but the spread you would expect to see in the population. So again, although the amount of error will vary from point to point, so some data points in your scatter plot will be farther away from the regression line, some will be closer. On average, the errors will be directly related to the magnitude of the correlation. So as your correlation gets closer to 1 or -1, and the data points are all very close to the regression line, so there'll be a small standard error. So as your correlation gets stronger, your standard error gets smaller. As your correlation, again, gets closer to 0, then your data points are not really going to be clustered around the regression line because they're more spread out. You're going to have a larger standard error of the estimate. So the calculations for the standard error of the estimate are right here. The standard error of the estimate is abbreviated SEE, and you find that by taking the square root of this thing called the sum of squares residual, which I'll get to in a minute, divided by the degrees of freedom. And I rewrote this formula this way just because degrees of freedom for regression is equal to n minus 2. So the same calculation for degrees of freedom that you had for correlation. Now, the sum of squares residual. There's two different ways to calculate this. This one conceptually makes more sense because we're really looking at averaging the difference between each actual y value in our data set and the predicted y values based on a regression equation. And just like when we talked about the conceptual formula for sum of squares, you square those values so that you don't end up with a value of 0. Because if you just did this, if you took each y and subtracted its predicted value and added that together, you'd end up with 0 every time. So the way that you would work this formula, you would take each y, subtract its respective predicted y value based on the regression equation, square it, then add it together. I'm not even going to demonstrate this formula because it's more error prone, it takes more time, and typically we are already going to have our r squared because we already did our correlation, so this formula is a heck of a lot easier and it's less error prone. But I did want to show you this because conceptually it makes sense. The sum of squares residual tells us the unpredicted variability. Well, if we're looking at the difference between the actual y value and the expected y value, those are the variability that isn't predicted by the regression equation. Okay, so moving on to the formula that you'll actually use in practice. So this 1 minus r squared gives you the proportion of variability in y that's not predicted by the relationship between x and y. So think about r squared, our effect size, and think about it in terms of the correlation. So r squared tells you the proportion of variability, or the proportion of differences in y that are predicted by the relationship between x and y. Well, remember, a proportion can never exceed a value of 1. And 1 would represent the proportion of variability in y that's not predicted by the relationship between x and y, and the proportion of variability or differences in y that is predicted by the relationship between x and y. You add those two things together, you would get 1 every time. Well, if you take 1 and subtract the proportion of variability or differences in y that is explained by the relationship between x and y, you're left with the proportion of variability or differences in y that's not explained by the relationship between x and y. So that is what this 1 minus r squared equals. Again, it equals the proportion of variability or differences in y that's not predicted by the relationship between x and y. And then you multiply that by the variability of y. So how much of the variability of y is not predicted by the relationship between x and y, multiplied by the variability of y, and you're left with the unpredicted variability. Then you plug that into your sum of standard error of the estimate formula, and it gives you kind of an average unpredicted variability among all of the values in your data set. And you divide by n minus 2 instead of just dividing by n. So this is kind of like a sample standard deviation formula. So remember, standard deviation is the square root of the sum of squares divided by degrees of freedom. And remember, I told you earlier, the standard error of the estimate is kind of like a standard deviation because it tells you the spread of data points from the regression line. And just like when you calculate the standard deviation for your sample, you divide by degrees of freedom to kind of bump up the overall value because you know that the sample is probably going to underestimate the true spread of data points from the regression line. So by making your denominator a little bit smaller, you're bumping up that overall value to compensate for the fact that you know if we did it with sum of squares residual divided by n, it would underestimate the true spread of all the data points in the population if we had them from the regression line. There's a whole theoretical reason why we use specifically n minus 2, but I'm not going to get into that. I just want you to know that we divide by degrees of freedom to bump up the overall value to compensate for the fact that we know that the spread of data points from the regression line in our sample is going to underestimate the true spread of data points in our population from the regression line. Okay. Enough about that. Let's go ahead and calculate the standard error of the estimate. So keep in mind that when we figured out the correlation between expected and actual quiz grades, it was 0.661. So I've got that on the screen. Let's go ahead and just use this formula. It's really simple once you know the correlation. So this will be 1 minus 0.661 squared multiplied by sum of squares y, which I forgot to put that here. We figured that out already when we did our correlation, and the sum of squares y was equal to 213.2. So 213.2. All right, so 1 minus 0.661 squared multiplied by 213.2. So this becomes 1 minus, so 0.661 squared gives you 0.4369. 0.4369 multiplied by the sum of squares y, 213.2. So right now, I know that my effect size for the relationship between expected and earned quiz grades is 0.4369. So if I turn this into a percent, I could say 43.69% of all the differences in earned quiz grades can be attributed to the relationship between earned and expected quiz grades. 1 minus 0.4369 gives you 0.5631. So if we multiply this by 100 to turn it into a percent, which is just more interpretable, right now 0.5631 is a proportion. But if we turn it into a percent, we can say 56.31% of all the differences in earned quiz grades cannot be attributed to the relationship between earned and expected quiz grades. Multiply that by the variability or the differences in the overall differences in earned quiz grades, and you end up with a sum of squares residual of 120.053. 120.053. That is sum of squares residual. I'm going to abbreviate resid. There we go. But we're not done. That's not the standard error, which wouldn't make sense anyway if we look at this. It doesn't make sense that based on this, we think that our predicted values for earned quiz grades are going to be 120 points away from the actual earned quiz grades. That doesn't make sense. we need to put it in terms of a rough average while correcting for the fact that we know we're going to underestimate it by dividing by degrees of freedom. So SEE. We also have to unsquare it too, because this is in terms of squared values. If you look at the conceptual formula, we had to square all those differences and add them so that we didn't end up with 0. So here we're working with an r squared as well. So we need to unsquare those differences by taking the square root. Okay. So this is equal to the square root of 120.053 divided by n minus 2. Well, n in this case was 5, and 5 minus 2 is 3. If you don't want to show that step, you don't have to because it's pretty easy math. This becomes the square root of, so 120.053 divided by 3 is 40.0177. And you end up with a standard error of the estimate of 6.326. So that makes a lot more sense given our picture of our scatter plot and our regression line. And what this tells us is that if the regression equation was used in the population to predict earned quiz grades based on expected quiz grades, we would expect that the predicted values for earned quiz grades would be about 6.326 points away from the actual earned quiz grades in the population on average. So this is the difference we would expect to see if we could collect data in the population between the grade that they actually earned and the grade that we would predict they would earn based on their expected quiz grades. Okay, now let's do hypothesis testing with regression to see if we're confident in using the regression equation that we came up with in the population to predict expected quiz grades, to predict earned quiz grades based on expected quiz grades. Okay, so I'm going to do step 3 first because much like when we did analysis of variance, we're going to be calculating an F statistic, and we're going to need to use the F table that we used for ANOVA to find our critical value in step 2. And to find our critical value, we need to know our degrees of freedom numerator, which now is degrees of freedom regression, and our degrees of freedom denominator, which is now going to be referred to as degrees of freedom residual. So I'm doing step 3 first. And I like to get my math out of the way. It's the fun part, but I still like to do it first. Okay, step 3. So you'll find these formulas in your formula sheet under the heading Analysis of Regression, but we are going to be finding an F statistic at the end. Okay, so let's go ahead and do the same type of process we did with ANOVA. Start with sum of squares total, work our way up, and then move on to the easier calculations, the degrees of freedom, and mean squares and F. Also, just like ANOVA, mean squared is the variance, and you find that by taking the sum of squares divided by the degrees of freedom for regression, sum of squares divided by degrees of freedom for the residual portion, and then F, you take mean squares regression divided by mean squares residual. And one thing that I want to point out, I said mean squares is variance. So the mean squared regression, that's the variance predicted by the regression equation. So the changes in y when x increases or decreases. Then the mean squares residual is kind of like the mean squares error of this. Just like remember mean squares within was the error variance in ANOVA. Well, the mean squares residual is the variance not predicted by the regression equation, or the changes of y independent of x. So it's pretty similar to ANOVA conceptually. Okay, let's go ahead and do our calculations. So starting with sum of squares total, that's equal to the sum of squares y, and that's something that you will have already found when you did your regression equation, and actually when you did your correlation. Okay, so I'm going to rewrite my source table here. So my regression, my residual, and total. And just like before, total is really there just for you to kind of check your work. All right, sum of squares, degrees of freedom, mean squares, and F. Okay, so I'm just going to rewrite for my sum of squares total, my sum of squares residual. I'm sorry, my sum of squares y. 213.2. All right, sum of squares residual. Guess what? If you've already found your standard error of the estimate, you've already found your sum of squares residual. So remember, we calculated sum of squares residual to plug into our formula for the standard error of the estimate. So I already know that it's 120.053. So 120.053. Well, if the regression portion of this equation is all about the variability that is predicted by the regression equation, so this is the variability not predicted, we want to know the variability that is predicted, so then we can divide it by degrees of freedom and find the variance that is predicted by the regression equation. Look at the formula here. So here we're looking for the proportion of variability not explained by the regression equation. Here we're looking for the proportion of variability that is explained by the regression equation. So it makes sense that this plus this gives you this, the total. Because remember, if you add these two together, you're going to get 1. So if you add these two together, you're going to end up with whatever SSY is equal to. So I'm going to do this calculation down here. Sum of squares regression, just so my table stays nice and neat. So R squared multiplied by the sum of squares y. So R was 0.661 multiplied by sum of squares y, 213.2. 0.661 squared gives you 0.4369. Multiply that by 213.2. And you end up with the sum of squares regression of 93.147. So plug that into your table, 93.147. Okay, my degrees of freedom. For our purposes, degrees of freedom regression is always going to be 1 because we only have one predictor in our model. We only have one x variable in our model. But I do want to mention that regression is a really powerful tool that can be used to predict a value for y or predict the value for your dependent variable based on many, many, many independent variables. So just for instance, I'm going to go off on a tangent for a second. There's something called multiple regression, and that's what I'm talking about. You can use multiple x's to predict multiple x's to predict a y. So instead of just having, y hat equals bx plus a, you could have y hat equals b1 times x1 plus b2 times x2 plus b3 times x3 plus a. So however many x values you'll have, you would have different regression weights for all the different x values in your equation. So think about how powerful that is. So for instance, if I was an insurance salesperson or if I was in charge of setting the premiums for car insurance, I could plug in tons of different variables that would help me predict how much I should charge somebody based on their risk. So not just age, which is an example that I talked about in the correlation example, but you could also look to see what should their expected or what should their risk or their premium be for insurance based on age, based on their credit score. That's actually something that people use because it's an indicator of responsibility. They figure if you're responsible with your finances, you'll be responsible on the road. Number of DUIs, right? You could also have number of speeding tickets. You could also have, all sorts of different things that you could plug into a regression model to predict how much should we charge this person for insurance. So regression is awesome. Okay, but we're only going to keep it in its simplest form for this class. This is an introduction to statistics. If you took a graduate level statistics, you would do regression for a whole semester. Okay, n minus 2, that's just going to be 5, so I'll write this, 5 minus 2 is 3, and 5 minus 1 is 4. And just like before, check it out. Sum of squares regression plus sum of squares residual, that gives you the sum of squares total. So this is the total variability in y. This is the portion that is predicted by the relationship between x and y or by the regression equation. This is the proportion that's not predicted by the regression equation or the relationship between x and y. Add those two together and you get the total variability in y. Then mean squares. So let's go ahead and I'm going to do these calculations over here. Well, the mean squares regression, I could do that without even writing it down. It's 93.147 divided by 1. So guess what? It's still 93.147. Keep in mind, if we were doing multiple regression, this degrees of freedom would not be 1, but for our purposes, we're only going to do regression with a single x variable. So this will always be 1 for us. That's why I just put a 1 there. Mean squares residual. So the variance not predicted by the regression equation, 120.053 divided by 3, and you end up with 40.018. 40.018. I'll just write that here, 40.018. Well, for f, just like in ANOVA, you take your mean squared, now regression, divided by your mean squared residual in this case. So 93.147 divided by 40.018, and I end up with 2.328. 2.328 for my final value for f. All right, now let's move on to see if this is significant. Well, step 1, the expected quiz grades are not a significant predictor of earned quiz grades. That's your null. You could also state this as the regression equation does not predict a significant amount of variance in earned quiz grades. You can do it either way. If you're doing multiple regression, you always want to state it in terms of the regression equation because there's multiple predictors, and the significant test doesn't tell you which predictor is significant, just like ANOVA, it just tells you that at least one of them is. But we're not going to go there. So you can state it like this. The independent variable is not a significant predictor of the dependent variable for your null. And then your alternative, your independent variable is a significant predictor of whatever your dependent variable is. Just make sure that you actually label your independent and dependent variables according to what they actually are in the problem. You actually write this out in words. This is the scientific way to do it. I would also accept if you wrote it in symbols. If you wrote, for instance, y hat is not equal to y, and then for alternative, y hat is roughly equal to y. The reason that they don't typically do this is because, remember, it can still be significant and there can be error between y hat and y, the predicted and the actual. But I just wanted to write that down to show you conceptually that's pretty much what we're saying. There's not a significant difference between the predicted and the actual y values, according to the alternative. And according to the null, they're not equal, right? There is a significant difference between what we would predict their value to be on the dependent variable and what their actual value is. All right. Step 2 is just like ANOVA. I'm not even going to walk through it because we've done this before. You would find 1 for degrees of freedom numerator, 3 for degrees of freedom denominator, alpha level 0.05, and you would have this critical value. 1 and 3, numerator, denominator. And if we drew this out, which I like to do, we're still working with the F distribution like we did in ANOVA. And so 10.13 would be like way out here. 10.13. It's a really large critical value because we have a really small sample size. Okay, in this case, let's go back and look. We calculated F to be 2.328. 2.328. Guess what? It's not making the cut. It's not in the critical region. So we would fail to reject the null. And as you see here, you can state this 2 ways. You can say results suggest that the regression equation does not predict a significant amount of variance in earned quiz grades, or you could just say expected quiz grades are not an accurate and significant predictor of earned quiz grades. Either way you state it is totally fine with me. They're essentially saying the exact same thing. So in other words, the predictions of earned quiz grades are likely based on sampling error and not a true relationship between earned and expected quiz grades. All right, now let's do an example problem where we find the correlation, regression equation, and standard error of the estimate for the regression equation, and then test the significance of the regression equation to see if it predicts a significant amount of variance in y. Let's go ahead and start by finding the correlation here between GPA and performance. So a lot of companies will use GPA as a selection tool. to predict the performance of new hires. But it's important to see if there's actually a relationship here. And if there is, then you can use GPA in a regression equation to predict someone's performance evaluation score. Now, much like the example I mentioned earlier about multiple regression and car insurance premiums, there's tons of different X values or predictors that employers, if they're doing data-driven selection, which I hope they are, that they can enter into their regression model to predict the performance of any prospective employee. So not just GPA, but maybe their scores on a personality test, or their scores on a work sample, or maybe a cognitive ability test that they took, their score on that. Maybe they have a standardized metric for rating references, calls to references, or a whole host of things that can be plugged into a regression equation to predict what their performance evaluation score would be later. Okay, power of regression. It's a beautiful thing. So I'm going to write down my formulas to figure out the correlation after I plot it in a scatter plot. So GPA and performance. So we have a range between 2 and 4. So let's just go ahead and do 2, 2.5, 3, 3.5, and 4. That makes sense based on the values I'm given. Performance ranges from 4 to 7. So let's just do 4, 5, 6, and 7. All right. GPA of 2, they had a performance of 5. GPA of 2, performance of 4. GPA of 3, performance of 6. GPA of 3.5, performance of 7. GPA of 4, performance of 7. This looks like a really strong positive relationship. If I drew a circle around these, it's very narrow, it's very linear, and they definitely go in a positive direction. All right, calculations. So to find my correlation, I'll write down that formula. And this should be review, so I'm going to fly through this. You've done several correlations by now. So sum of products. And then writing down my formulas for sum of squares x and sum of squares y. Sum of x squared minus sum of x squared over n. Sum of y squared minus sum of y quantity squared over n. Okay, so plugging in my values, I'm just going to work through this real quick. Sum of x, y, or sum of y squared, 175, minus sum of y, 29 squared, divided by 1, 2, 3, 4, 5 people. So 175 minus 168 point, oh wait, I'm going ahead of myself, 841 divided by 5. Becomes 175 minus, so 841 divided by 5 gives me 168.2, and you have a sum of squares y of 6.8. Always underline your answers because we're going to be using these time and time again for all these calculations. All right, sum of squares x. So sum of x squared, 45.25 minus 14.5 squared divided by 5. 5.25 minus, so 14.5 squared is 210.25. Okay, and we end up with 3.2 for sum of squares x. Sum of products. All right, so 88.5 minus 14.5, 29 equals. All right, got our sum of products. Now I'll plug this in. All right. And we have a correlation of 0.943. It's super strong. And yes, it is positive. Okay. Now, I encourage you to pause and try it before I show it to you, especially on these next ones. This should just be completely a review for you. But for the regression, for these next steps, I want you to pause it before I work it out. Try it yourself, and then use this video to check your answers and make sure that you did it correctly. All right, so next step. The regression equation, then using the regression equation to predict the job performance of someone with a GPA of 2, and then on average, how far off will predictions of job performance be based on GPA? If you see something that's asking you a question like that, how far off will the predictions be? You are being asked for the standard error of the estimate. Keep that in mind. All right, pause it and try it for yourself, and then resume it and see how well you did. Okay, so let's figure out our regression equation. So we need to know y hat equals something, b, times x plus something, our a. So let's figure out b first. So b equals, so I'll just put it there, bx plus a. We're going to find that. So remember, the formula for b is sum of products divided by sum of squares x. Sum of products divided by sum of squares x. Well, I wrote down what we found before. We found our sum of products to be 4.4. Sum of squares x was 3.2. 4.4 divided by 3.2 gives you 1.375. That's our b. Now a is equal to the mean of y minus b times the mean of x. And the mean of y and the mean of x are right here. So 14.5 divided by 5 gives you 2.9. 29 divided by 5 gives you 5.8. All right. So the mean of y, 5.8, minus b, which we just found to be 1.375, times the mean of x, 2.9, becomes 5.8 minus 3.9875, and you get 1.813 for A. Now we can plot, or now we can talk about our regression equation. All right, so B, so y hat, our predicted performance is equal to 1.375 times x, whatever their GPA is, plus 1.813. So in other words, for each point increase in GPA, we think that their performance evaluation score is going to increase by 1.375. And if somebody had a GPA of 0, we would expect their performance to be 1.813. This is like the starting point for performance. So we're done with part B. So part B. Now let's do part C. So what would we think somebody's job performance would be in the population, any employee that could be hired, if their GPA was 2? So y hat, their predicted performance, is equal to 1.375 times 2 plus 1.813. So this becomes 2.75. So 1.375 times 2 is 2.75 plus 1.813. And we have a predicted performance score of 4.563. So if we look at this value, it's in between the observed y's when x equals 2. So let's go back and look. These two people have a GPA of 2. This one actually had a performance of 5. This one had a performance of 4. And our predicted value in the population for somebody with a GPA of 2, their predicted performance is 4.563. So right between 5 and 4. All right. Now let's go ahead and plot this bad boy in our scatter plot. Why not? So for a GPA of 2, we have 4.563 is our predicted value. I'm just going to go and do a little extra and find, if somebody had a GPA of 4.0, what would it be? So 1.375 times 4 plus 1.813. So 1.375 times 4 gives you 5.5 plus 1.813 equals 1.813. 7.313 would be their performance evaluation expectation. Now, let's go back. Okay, so yeah, 7.313 is above that performance for somebody with a GPA of 4 in our actual data set. But let's go ahead and plot this out, just as an extra step. So remember, for a GPA of 2, we expected 4.563. So 2, 4.563, right around here. And then for a GPA of 4, 7.313. So 4, 7.313. If we draw that, look, it's in between our data points, just like last time. All right. So this is just an extra part. All right, part D. On average, how far off will the prediction of job performance based on GPA be, the standard error of the estimate? Well, I'm thinking right now I'm going to have a pretty small standard error. My correlation is really large. Remember, the correlation was equal to 0.943, so it's a very, very, very strong relationship. And when I plotted my data points out, all the data points are pretty close to the line. So I'm thinking this regression equation is going to be pretty good. But let's figure out how far off we think our estimate would be. So let's write down my formulas. Standard error of the estimate is equal to the square root of sum of squares residual divided by the degrees of freedom. Well, I don't know what my sum of squares residual is, so it's time to write down another formula. And sum of squares residual, I'm going to use the 1 minus r squared times sum of squares y formula. So this becomes 1 minus 0.889 multiplied by the sum of squares y, which I totally didn't write down up here. Let's go back and see what it was. 6.8. So 1 minus 0.889 gives you 0.111 multiplied by 6.8, and you get 0.755. So, sum of squares residual. All right, now let's plug that in the standard error of the estimate. 0.755 divided by degrees of freedom, n minus 2. 5 minus 2 is 3. This becomes the square root of 0.252, and you have a standard error of the estimate of 0.502. 0.502. All right. So on average, we suspect or expect that the performance evaluation score that we predict for somebody based on their GPA will be off by about 0.502 points. That's the standard error of the estimate. Now let's find out if this regression equation is actually significant. Okay, so starting off with our sum of squares total is equal to the sum of squares y of 6.8. Then our sum of squares residual, we already found that. You know what? Let's go ahead and erase these. Go away. Let's put these things in a source table. So source, regression, residual, and total. And again, I hope you're pausing these videos and trying this out before you watch the answers. All right. Sum of squares, degrees of freedom, mean squares, and F. And I'm starting with step 3 again, just because we need our degrees of freedom for step 2 anyway. So sum of squares total, again, remember it's just equal to sum of squares y, which is 6.8. Sum of squares residual, so what we already found, 0.755. You're not always going to find the standard error of the estimate before you do your hypothesis test, but if you do, you don't have to do the calculations for sum of squares residual again. Now, sum of squares regression, I could take r squared and multiply it by sum of squares y. So 0.889 multiplied by 6.8, and I end up with, for sum of squares regression, 6.045. But remember with ANOVA where you could find the sum of squares between by taking the sum of squares total and subtracting the sum of squares residual? Well, if you take 6.8 minus 0.755, you end up with 6.045. Either way you want to do it, totally fine with it. So 6.045. So we can say or sum of squares total minus sum of squares residual equals 6.8 minus 0.755 equals same exact thing you got there. All right, next step, degrees of freedom, boom, 1 automatically for regression. Degrees of freedom residual, n minus 2, 5 minus 2 is 3, and then 5 minus 1 is 4, 1 plus 3 is 4. Hooray! Mean squares regression. You just transfer over the sum of squares regression because we're doing single x value regression here. Then the mean squares residual is equal to 0.755 divided by 3. And 0.755 divided by 3 gives you 0.252. So record that here. And then F, your mean squared regression divided by your mean squares residual, 6.045 divided by 0.252. Oh, sorry, 2.52. Go away, you. So 6.045. Oh, no, wait, it is 0.252. What am I doing? Okay. 0.252. 0.252. All right, we're good now. 6.045 divided by 0.252 gives you a huge 23.988 for your F. 23.988. Oh my goodness. All right, moving on to the rest of the hypothesis test. Step 1, regression equation does not account for a significant proportion of the variance in performance. That could be your null. Or you could say that GPA is not a significant predictor of performance. Got an extra dot there. Oh well. Alternative, what we expect is that the regression equation does account for a significant proportion of the variance in performance. Or in other words, GPA is a significant predictor of performance. Step 2, draw this out. You've got the same critical value that you had before. This is always going to be 1, your degrees of freedom numerator. And our degrees of freedom denominator, or our degrees of freedom residual, was 3 again because we had 5 people in our sample. And if we go back and we look at 23.988 is our observed F. 23.988, way out there. Huge, huge, huge F value. So we know that there's a lot more variability in y that's being predicted by the relationship between x and y, or in this case the regression equation, than the variability that's not being predicted by the regression equation. So we reject the null, and we are supporting the alternative saying the regression equation predicts a significant amount of variance in performance, or in other words, GPA is a significant predictor of performance. All right, guys, that is regression. You can see why it's in the same chapter as correlation. It's very strongly related to correlation. And just keep in mind, if we're looking for the relationship between two variables, correlation. If we're using X to predict Y, or we're making predictions, regression is what you want to use.